Okay, so today we're going to talk about useful counting rules. This is section 3. So we're all familiar with just basic counting, which is like 1, 2, 3, 4, 5, 6, and so forth. But what I want to do is go ahead and show us techniques on counting that allow us to find our sample size very quickly. So, many of us in this room, you may have visited a restaurant called Subway. Okay? And I'm going to try to keep this as simple as possible. But if you think about what the process in which you go through at Subway, all right, it's you walk in, you walk up to the line, and usually the worker says, welcome to Subway. What kind of bread would you like? And the bread options at Subway, are like whole wheat, Italian bread, that Italian herbs and cheese bread and stuff like that. But what you notice is there are 5 types of bread. Okay, so then the next thing they ask for is, what kind of protein do you want, or meat? We'll just call it protein. Okay, so from here you have options. So you can get like meatballs, you can get turkey, you can get ham. You can get a seafood, which is still considered protein. You could get all the a bunch of different chicken breast, all this different stuff, all these different types. So let's just say, for example, there are 10 different options for a protein. Then they ask you, do you want it toasted or not toasted? Well, toasted or not toasted, just 2 options. You either get it toasted or you don't. Okay? Then they ask you what type of cheese. I guess they ask you to cheese before toasted, but we'll just put cheese right here. And cheese, you have like provolone, you have American cheese, you have like a special blended cheese or something like that. But you notice there are 4 different types of cheeses you can get. Then you have the veggies. And the veggies, there's a bunch of veggies, okay? So we'll say there are basically 9 different types of veggies you can get, because you can get lettuce, you can get spinach, you can get onions, you can get banana peppers, you can get jalapenos, all these different ones, all right? And then they ask you, okay, well, what type of sauce do you want? And that could be like mayo or that like Chipotle stuff or chicken teriyaki. And there are 6 different types of those. So the question becomes this right here. How many different subs can we make here? Okay, how many different subs can you make? And you can have, and I'm just throwing this out there, you can have a sub that is only bread, cheese, and mayonnaise. That's considered a sub, so that's one of them. Or you can have a sub that has bread, one slice or one, provolone cheese, chicken breast, every single vegetable you can imagine, and just throw on all the sauces as well. That would be another sub. So the question becomes, how many different subs can you get? Now, to answer this question, we're going to use what we call the multiplication counting rule. Oh, forgot the word counting. The multiplication counting rule. Now, this rule says that for a sequence of events in which E1 or event 1 can occur N1 ways, and event 2 can occur N2 ways, and event 3 can occur N3 ways, and so on, the total number of ways, or how about just the total number of outcomes, is equal to N1 times N2 times N3 all the way up to NP ways. Okay? So what you would do is you would just keep multiplying these numbers together. So if we go back and we look at how many subs, so the total number of subs is going to be equal to, and I got to screw up here a little bit because I forget my numbers, 5 times 10 times 2 times 4 times 9 times 6. And that's going to equal 21,600 different subs, which is a bunch. All right. And like I said, you can have very extravagant subs, or you can have the very boring, I only want meatballs and nothing else, which is nothing wrong with that. I think it's a little boring, but that's just me. So let me show an example, another example of where this can occur, or we use this rule. How about that? All right, so here's our second example. So we're going to talk about phone numbers. Phone numbers are created using the following criteria. So the first is area codes use digits 2 through 9 for the first digit, and then 0 through 9 for the second and third digits. But the last two digits cannot both be 1. For example, I'm going to write it in red here. The number 911 is not considered to be an area code because this is considered to be like an emergency number. 411 also is not an area code because that's like an information number or something like that. Okay? So the question here is, how many area codes are possible with these rules? So the way to think about this is the exact way that the multiplication counting rule is defined. So what we're going to do is we're going to draw 3 lines, okay? And these 3 lines are going to represent every single, or just what an area code looks like. So we know for the first digit, only the numbers 2 through 9 are allowed in that very first digit. So if you think about it, there are 7 ways that can occur. Because if you think about it, you have 2, 3, 4, 5, 6, 7, 8, 9. And if you just count them, 1, 2, 3, 4, 5, 6, 7, 8. Oh, sorry, I wrote 7. I meant 8. My bad. All right. Now, for the next 2 digits, there is a rule that we need to apply. And I'm going to highlight the rule here. So the rule says for the second and third digits, both of them cannot be 1. All right? So what I'm going to do, what I'm going to do here is I'm going to assume that they're both going to be 1. Like I'm going to just make the assumption that they're allowed to be 1. So in that case, you have 10 options for the second digit and then 10 options for the third digit, okay? So as it looks right now, because I assumed that 1 is allowed to be there, we're going to have 8 times 10 to the second power, or 8 times 100, which is 800 ways, okay? But now if I think about it, the numbers I'm not allowed to have are 911 or 411 or any other one of those values. Now, because the first digit is only allowed to be 2 through 9, what we can do is we can start just writing out the ones we can't have. It's not much when you think about it. So you're not allowed to have 211, 311, 411, 511, 611, 711, 811, and 911. These are the ones you're not allowed to have. So if you just count them, 1, 2, 3, 4, 5, 6, 7, 8, what we're going to have to do is take our total value and just subtract 8 from that. So I'm just going to erase this real quick. Subtract 8 because those are the numbers I'm not allowed to have. And that gives me a grand total of 792 different possible area codes that we can have. All right? Now for the second part, the same rule applies to exchange numbers. Now, the exchange number are those 3 digits before the last 4 digits. So they're like the ones scrunched in the middle, okay? And I'll go ahead and write it out for us. So the same rule applies to the exchange numbers. Given both of those rules, how many 10-digit phone numbers are possible? So let me go ahead and write this out here. So the first 3 digits are always your area code. Then the next 3 digits, those are your exchange numbers. And then the last 4 digits, I don't even know if they have a special name. I think they're just there just to go ahead and differentiate. So what this question is saying, the same rules apply to the exchange number. So here's what we know. Possible area codes. 792 ways we can make area codes. And those rules also apply to exchange rules. So there are 792 ways that we can form exchange rules. The last 4 digits, there are no rules for that. So there are 10 possible numbers for the first, 10 possible for the second, 10 for the third, and then 10 for the fourth. So how many 10-digit phone numbers are there? Well, the number of phone numbers is going to equal 792 times 792 times 10 to the 4th power. So if you go ahead and just take that, 792 times 792 times 10 to the 4th, you're going to get, give me a second, 627264 with 4 zeros. Now, put some commas in there. So this is going to give us 627,206. Oh, geez. Apparently I can't count. There's even more. Sorry about that. Let's try that again. There are 6,272,640,000 possible phone numbers. Now, these rules that we were talking about here apply to they apply to the United States and Canada, just basically North America. And the total population for the United States of America and Canada is approximately 400 million people. So we are not going to run out of phone numbers anytime soon. In fact, what ends up happening is people with phone numbers, and when they die, they just get recycled. It's just, I think the phone company, they may have like a 15-year wait on that number before they put it back in circulation. Maybe it's 15 years, maybe it's 10 years or something like that. I don't know. Same thing happens with Social Security numbers, though. They just recycle them after a certain amount of time. They just wait until that number has not been used for a duration of time before they go ahead and reintroduce it. So I just gave us 2 examples of using this counting rule. And the thing to remember is you got to figure out how many ways can the first event occur, and then how many ways can the second event occur, and so forth. Now, sometimes, you can't really use things that you used previously. And what I mean by that, okay, is let's think about a race, okay? So a horse race is about to occur. And the horse race has 10 different horses. The question becomes, how many ways can the horses finish? All right, so if you think about it, there are 10 horses, and you have a first place horse, then you have a second place horse, and a third place horse, a fifth place, 6th, 7th, 8th, all the way down to 10th. So when we look at this problem, it's still a counting problem. We're still using the multiplication counting rule. We're just going to draw 10 little dashes here. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there are 10 dashes. All right, and here's first place. Here's second. And all the way on the end, here's 10th place, okay? And if you think about this, there has to be a winner and there has to be a loser. And there has to be ones in between. So the number of ways that we can get a first place finish is 10. But then once that horse wins, you can no longer use that horse. So the number of ways that second place can occur is going to be 9. And then the number of ways that third place is going to occur will be 8. And then fourth place will be 7. Fifth place is 6. Sixth place is 5. Seventh place is 4. Eighth place is 3. Ninth place is 2. And then you have the last place horse. So if we were just to take this value, 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, you would get this number here. So there are 3,628,800 different ways that these horses can finish. Now, this is a very specific type of problem. If you notice in the previous problems, all right, we were just looking at the number of ways that each event can occur, and sometimes there was like a little rule. But in this case right here, every single horse, once they have their place, you can no longer use that horse. So we call this, whenever you have a sequence of numbers that are just going down by 1, we call this 10 factorial. And that exclamation point stands for a factorial. Now, a factorial in general, n factorial, is defined as n times n minus 1 times n minus 2, and you keep multiplying until you get down to 3 times 2 times 1. So that's what a factorial is. So if this definition kind of looks a little crazy, all you have to do is just substitute a number, like 7 factorial, and just substitute in the values. So we get 7 times 7 minus 1, 7 minus 2, 7 minus 3, 7 minus 4, 7 minus 5, 7 minus 6, and then you would be done here. Because if you just simplify each set of parentheses, you have 7, 6, 5, 4, 3, 2, and 1. So that's how this definition above works. Now, there is one special factorial. 0 factorial equals 1. Okay? Excuse me. And I can show you why it equals 1 just by kind of doing like a little... this is not like a rigorous math proof, but it's good enough for us right now. So here's what we know. We know 0 factorial. Actually, let me start even more general. We know that n factorial is going to equal n times n minus 1 factorial, meaning this is just going to repeat n minus 2, n minus 3, n minus 4, n minus 5, until you get all the way down to whatever number you want to stop with, okay? Now, there is one special rule in mathematics. It's called the division property of equality, but basically, you know what this rule is. Whatever you do to one side of the equation, you do to the other side of the equation. So, I can divide both sides of the equation by n if I want to. Now, on the left-hand side of the equation, you get n factorial divided by n. However, on the right-hand side of the equation, notice that the n's reduce. And you're going to be left with n minus 1 factorial. So now, if I let n equal 1, on the left-hand side, I get 1 factorial divided by 1 equals the quantity of 1 minus 1 factorial. Now, 1 factorial is 1, over 1 is 1, so on the left-hand side you get 1, and on the right-hand side, 1 minus 1 is 0 factorial, which is exactly what we wanted to show. 0 factorial equals 1. So now, hopefully you can see how this factorial rule kicks in when we have objects that are no longer repeating, okay? So let's look at another example here. Okay, so a statistics researcher must visit the presidents of the following polling companies. So you have Gallup, Nielsen, Harrison Pugh, and Zogby. How many different travel arrangements can be made? So the driving force behind this question is the fact that we are bombarded with stats every single day, whether it's in sports or politics or science, and there are companies that actually help to collect data. The question becomes, are they collecting the data responsibly? I always get a little laugh at the toothpaste commercials. 4 out of 5 dentists recommend. Well, where are you getting the dentist from? That's my first question. Are these dentists that happen to also be researchers on your staff, or did you go and sample 100,000 different dentists throughout the entire United States using a simple random sample? Or did you just drive down to the city that you're located in for convenience, hence the convenience sampling from back in like chapters 1 and 2? So all that stuff kicks in, and whenever I start seeing stats being thrown in my face, the first question I always ask myself is a very simple one. Where did you get the numbers from? Where did you sample from? Because I just want to make sure that they're doing their job and giving me an unbiased result. And let's be honest, that rarely ever happens. So good luck trying to figure that out. Anyways, the question here is how many different traveling arrangements can be made? So if you think about this, once this researcher visits Gallup, they no longer have to go to Gallup. And once this researcher goes to Nielsen, they no longer have to go to Nielsen. So the number of ways that this can actually occur, excuse me, is just going to be counting up the different polling companies. So we have Gallup, which is 1, Nielsen 2, Harrison Pugh is 3, and then Zogby, which is 4. So this is going to be just 4 factorial, which is 4 times 3 times 2 times 1, or 24 different ways. Now we could extend this problem a little bit further because right now, remember, we're trying to just count things. But I could ask this question, so this is a follow-up part B. What is the probability that the presidents are visited in order from youngest to oldest? So now we're actually thinking about probability. So we want probability of young to old. And remember, probability, the number of ways the event can occur divided by the total sample space. So let me go ahead and write that out. Number of ways from young to old divided by the total sample space or total outcomes. Well, there is only one way that you can arrange these presidents from young to old. So there's only one way you can do that. And how many total outcomes are there? Well, how many different ways can you pick travel itineraries? Well, in this case, it's going to be 24. So if you just do the math, 1 divided by 24 is approximately 0.042, or we'll just call it 4.2%. So the probability that the trip that you picked just happens to be youngest to oldest is 4.2%. Likely not going to happen. All right, so just to sum up everything that we've done so far. 1, we've learned the multiplication counting rule. All right, and that's just basically E1 times E2 times E3 and so forth. In other words, the number of ways that event 1 can occur times the number of ways event 2 can occur times the number of ways event 3 can occur, all the way down to the number of ways that event P can occur. Okay, however many events. Sometimes you may have like specifications on these events, such as, for area codes, the first digit cannot be a 0 or a 1, so you have to adjust accordingly. Then the second way we learned is this factorial rule. And what really made this special is there was no repeating in it. For example, if we were to pick this travel itinerary, once you visit one state or one company, you don't go back to it. So there is a natural order to this. All right, so this would be n factorial, which is n times n minus 1 times n minus 2, and you just keep doing this until you get down to 3 times 2 times 1. Okay? So now we're going to talk about the third rule. Okay? And this third rule deals with what we call permutations. Okay? Now, this third rule, there's kind of like, if I were to say, it would be like an A and a B. So the first one we're going to worry about is this. So here's the conditions. When all of the items are different and order matters. Okay? So when all the items are different and order matters. Now there is a formula for this, okay? And the formula looks like this. So NPR, or the number of permutations for the objects chosen, is equal to n factorial over the quantity of n minus r factorial. So n represents the total outcomes, or total possible, we'll say. Total possible. R, sometimes you see a letter C here, stands for the number chosen. And all you do is kind of just substitute into this formula. Now, we'll do an actual example using this. For now, I just want us to get comfortable with using the formula. So if we're looking at an example, just like something like this, like 7 permutation 3. Okay? So what that's going to mean is that we have 7 factorial over 7 minus 3 factorial. Now, if you were to write this out by hand, you would have 7 times 6 times 5 times 4 times 3 times 2 times 1, all divided by, 7 minus 3 is 4. So then you would have 4 factorial. So that would be 4 times 3 times 2 times 1. And you should notice that in that denominator, I kind of skewed it to the right. And there's a reason for that. It's because if you were to write all this out, 7 times 6 times 4 times 3 times 2 times 1 in our numerator, and then denominator would be 4 factorial. Notice that once you start doing all the multiplication, you have numbers that will reduce. So you have a 4 in a numerator and a 4 in a denominator. So they reduce. You have a 3 in a numerator, 3 in a denominator. They reduce. 2 in a numerator, 2 in a denominator. They reduce. And then lastly, you have a 1 in the numerator and a 1 in the denominator, and they reduce. Okay? So what you're left over with is just 7 times 6 times 5. And 7 times 6 times 5 is going to equal 210. So 7 permutation 3 equals 210. Now, This 210 represents what we call different permutations. So hopefully now you're sitting there thinking to yourself, okay, well, what do you mean by permutations? And this is what I mean by a permutation. Let's say we had 3 letters, A, B, and C, okay? How many ways can I arrange the letters? Oops, sorry. A, B, C. Okay? Well, if you think about this, what we have are 3 letters that we're picking. And in this case, order matters because I want to arrange these letters. And I'm choosing 3 letters. So if you were to do the math here, you would get 3 factorial over 3 minus 3 factorial, which is 3 factorial over 0 factorial. We know by definition, 0 factorial equals 1. So this is just 3 times 2 times 1 over 1, or just 6. So there are 6 different ways that I can arrange ABC, and they're different. And that's really important. So ABC does not equal CBA. In other words, these are 2 completely different things. All right? So if you wanted to, you can write these out by hand. And that would be another way to figure out how many ways you can arrange the letters ABC. So you can have ABC. You can have ACB. You can have BAC. You can have BCA. And then you can have CAB. And then lastly, CBA. And I think those are all the ones that you can have. And if you just count them up, 1, 2, 3, 4, 5, 6, there's 6 of them. But like I said, now the question becomes, okay, what if you have a lot of objects, but you're only selecting a certain amount? That's where the permutation rule really kicks in. So let's look at another example here. All right, so here's our next example. And it's another horse race. I think horse racing examples are really good because there's a natural order to them. So in a horse race, a trifecta bet is won by correctly selecting the horses that finish in first, second, and third place in order. And I had to look this up, but in 2021, there were 20 different horses that ran in the Kentucky Derby. The first question is, how many different trifecta bets are possible? And then a follow-up question would be, what is the probability of winning that trifecta bet? So what is the probability that you selected first, second, and third place? So here we need to ask ourselves, is there a natural order? And the answer to that is yes. You need to pick first, second, and third place. So because there is a natural order, we're going to use our permutation rule. Okay? So let's set it up. 20, permutation 3. And so if you think about it, 20 total horses. 3, that's the number you're picking. So this is going to be equal to 20 factorial divided by 20 minus 3 factorial, which is equal to 20 factorial over 17 factorial. So to simplify this a little bit by hand, here's what I'm going to do. I'm going to write 20 times 19 times 18 times 17 factorial divided by 17 factorial. And the reason why I didn't write everything out is because I know in my numerator, once I hit 17 and then 16 and 15 and 14 and so forth, my denominator is going to automatically reduce itself. So I can go ahead, now that I have this set up, and I can scratch out the 17 factorial in the numerator and denominator and just take my calculator and do 20 times 19 times 18. So 20 times 19 times 18. And this is going to equal 6,840 ways. Okay? Now, if you happen to have a calculator that can do this, all you got to do is figure out, how do you input it. So for us, or for me personally, as you can see, I'm a huge Dragon Ball Z fan. So I have this little calculator here. All right, that it just emulates a TI-84. All right, I guess can I maximize that a little bit? There we go. I think that'll help. So for in the TI-84, what you're gonna do is you're gonna click on Math, and then you have Math, Numbers, Complex, and then Probability. So we'll just scroll over to Probability here, and then the second option is NPR, which stands for your Permutation Rule. So you can hit down or just hit the number 2. Oh, I don't know why it's giving me the answer. Sorry. So this is an older version. I have the newer one, and in my handheld one. So here's what we do: 20. Now you go ahead and click on Math, scroll over to Probability, scroll down to the Permutation Rule. So this is 20 NPR 3, and when you hit Enter, it gives you 6,840, which is exactly what we calculated. So that you can use a calculator if you want, or you can do it by hand. Both completely acceptable. But now the second part is, what's the probability of winning? Well, there's only one way that you can select the trifecta. There's only one way: first, second, third place. So this is going to be 1 over 6,840. And if you do the math there, you get 1.46 times 10 to the negative 4th. And I don't know if you remember how to convert between scientific notation, but basically, write 1.46. This negative 4 tells me to move my decimal place 4 places to the left. 1, 2, 3, 4. So I get an answer of 0.000146, or if you want a percentage, 0.0146%. In other words, the likelihood of you guessing the trifecta correctly is basically 0. It's so close to 0, it's ridiculous. And that's why if you nail it, you win an unbelievable amount of money, because it's next to impossible to win it. So now we do have like a part B to the permutation rule. So I'm going to put I'll put this in parentheses, like part B, okay? So this permutation rule man, I can't spell today. It's Sunday, and I'll be honest with you, I got the Steeler game on to my right here. So permutation rule, and this rule kicks in when some of the items are identical. When some items are identical. So order still matters. I mean, that doesn't go away. It's just some of the items are the same. All right. So, for example, if you have 9 different cookies. Now I'm starting to get hungry. And here they are. You got 4 chocolate chip, which are, I think, my favorite. 3 oatmeal. And then 2 raisin cookies. Gross. How many different orders can you eat all of them? All right. So in this situation here, order still matters. However, you have cookies that repeat themselves. You have the same type of cookie. So we have 4 chocolate chip, 3 oatmeal, and 2 raisin. Now, in order for us to do this, like I said, we're going to use what we call a permutation rule when items are identical. All right. And that rule looks like this. So when order matters, and identical items is going to equal n factorial over n1. Come on, work with me, pen. n1 factorial, n2 factorial, and you just keep doing this all the way down to np factorial. Okay? So for our problem, here's how it's going to work. We have 9 factorial in the numerator, because that's the total number of cookies that we have. However, we have 4 chocolate chip cookies, so that's going to be 4 factorial, times 3 factorial, because we have 3 oatmeal cookies, and then 2 factorial, because we have 2 raisin cookies. And that's going to equal 1,260 different ways that you can eat these cookies. Okay? Now, if you wanted to use your calculator with this, that's 100% okay. Let me show you. So, underneath the math menu again, underneath probability, you're going to see option 4 is the factorial button. So the only thing that you really need to be careful with, all right, is just typing this into your calculator. So what do I mean by that is this. You got 9 factorial in the numerator. Now you need to divide that by 4 factorial times 3 factorial times 2 factorial. However, the 4, 3, and 2 are all in the denominator. So we're going to put it in parentheses. So parenthesis 4 factorial times 3 factorial times 2 factorial. End the parenthesis. So this is going to tell the calculator all 3 of those values are in the denominator. If you do not do that, you are going to get this answer wrong. I guarantee it. Okay, so you got to be careful about how you type it in. So then you just hit enter, and there's our 1,260 ways again. Okay, so remember, you want to use a calculator, I say go for it. I encourage it, but know how to use it. If you need help using it, all you got to do is ask. All you got to do is send an email. Professor Float, this is the calculator I have. Can you help me with it? And I'd love to. Okay? Now, the last counting rule that we're going to learn is when order doesn't matter. Okay? So this is our last one. So this is going to be combination rule. And the key to this rule is order does not matter. So ABC is the same exact thing as CBA. We don't care. Order doesn't matter here. Okay? So the formula for this is going to be NCR, and that's going to equal n factorial over n minus r factorial times r factorial. Okay? So I have an example for this, and then I'm going to just kind of like summarize everything that we've done so far. And that's going to be it for this video. So it's a long video, but I think each of the concepts kind of easy. So here's our example. Let me write it out. All right, so here's the last problem of the day. So Professor Float grades homework by randomly choosing 5 out of 12 problems. So what I did is I gave 12 problems, and I said, all right, I'm going to pick 5 of them, and those are the ones I'm going to look at. So question A, and there's 4 parts to this question, A, B, C, and D. So we're not going to rush. We're just going to do one part at a time. So first, just how many different groups of 5 problems can be chosen from 12? Now, if you think about it, order doesn't matter here. I'm just picking problems. So this is a direct connection to what we're trying to learn, which is the combination rule. So this is going to be 12, choose 5, which is going to be equal to 12 factorial over 12 minus 5 factorial, 5 factorial. Now I'll reduce it just a little bit here. So I got 12 factorial over 12 minus 5 is 7 factorial times 5 factorial. Now, from here, there's a lot you can do. You can write everything out if you wanted to, and you can start crossing things out. Or you can use a calculator to just simplify this. I'm hoping by now you are going to use a calculator. So let's go ahead and let's just use our calculator here one more time so I can show you. So in your calculator, you do have a combination function. So we're going to type in 12, hit our math button, go over to probability, and you can look, it's option 3 here. So it's going to be option 3. So 12 combination 5. And when you hit enter, you're going to come up with 792 different ways. So there are 792 different groups of 5 that I can select. All right. Now, part B, Arthur. It's my dog. That's our puppy's name. So Arthur did only 5 problems of the assignment. So Arthur's a bad student. Probably woke up the day that the assignment was due and said, you know what? I'm just going to do 5 problems. That's all I have time for. So Arthur did only 5 problems of the assignment. What is the probability that the problems he did are the same exact problems that Professor Float chose to be graded? So in this case, it's going to be P of Arthur. And actually, it's Arthur choosing correctly. I guess I can write that out. Arthur chooses correctly. Well, there's only one way that I selected these problems. Now, there were a total of 792 different groups of 5, but only one of those groups is the one I selected. What is the probability that Arthur also chose the same? Well, it's going to be 1 over 792, which is approximately 0.001263 or 0.13%. Not even a 1% chance. It's less than 1%. So poor Arthur, he's probably just going to do really bad on this homework assignment. Well, he failed it because he's not going to guess it. But now we have another student. And in walks Ernie. Ernie is the name of one of our cats. So Ernie did 7 problems. So a little bit better than Arthur. Arthur only did 5. Ernie did 7. So the first question is, how many groups of 5 did he do? So this is going to be 7, choose 5, which is going to equal 7 factorial over 7 minus 5 factorial times 5 factorial. If you want to simplify this down a little bit, you can. It's going to be 7 factorial over 2 factorial times 5 factorial. And that's going to equal 21 groups of 5. So because Ernie did 2 more problems, there were 21 possible groups of 5 that he could have chosen. So part D is, well, what's the probability that one of the groups of 5 that Ernie completed is the same group as the ones that Professor Float scheduled to be graded? So in this case, we'll say P of Ernie correct is going to equal, well, how many different ways can Ernie pick his group of 5? Well, it's going to be 21 different ways over the total amount, which is 792 groups. So this is equal to 0.026515, or if we round to 1 decimal place, 2.7%. So just because Ernie did 2 more problems, the chances went up by a lot. However, it's still roughly 3% chance of actually getting the group that I wanted. So I guess the moral of the story here is, Professor Float assigns 12 problems. Just do 12 problems and you'll be fine. You'll always have the ones that I picked. Okay? So the last thing I want to do here is just give us just an idea of what just happened here, because this is if I'm looking at it, a 50-minute video right about now. It's a long one, so it's nice just to kind of wrap everything up. So here's like a little flow chart here. So anytime you're trying to count, this flow chart will actually help you. So this is our flow chart for counting. All right. So the first question you want to ask yourself is, does order matter? Okay. And if your answer is yes, let me write it up here. The next question you want to ask yourself is, are there repeated objects? Okay? And from here, you have two options. Yes or no. If the answer is yes, you have repeated objects, then you're going to use the n factorial over n1 factorial times n2 factorial, and you keep doing this for however many events that you have, or not events, but numbers, or repeated objects. Repeated objects. If the answer is no, then you use just the traditional permutation calculator or formula. Now, if the answer to your question, does order matter, is no, then it's just the combination rule. Okay? And that's going to be it for this video. So good luck learning how to count. I'll see you in the next one. Bye.